A very good morning to all of you. I welcome you all to the day 2 session on smart grid integration and energy storage systems. The chief guest of the day is Professor and Head of the Department, Dr. S.U. Prabha ma'am. The topic of today's session is renewable energy grid integration techniques and challenges. So I would like to introduce our Head of the Department, Dr. S.U. Prabha ma'am received her PhD degree in the year 2010 from Faculty of Engineering and Technology, Multimedia University, Malaysia. She received her ME degree in Electrical Machines from PSG College of Technology, Bharatiya University, Coimbotore, India 1997, and her BE degree in Electrical and Electronics Engineering from Coimbatore Institute of Technology, Bharatiya University, Coimbatore. She is having around 25 years of teaching experience and around a decade of research experience. She possesses 10 years of international experience in teaching and research. Currently, she is working as a professor and head in the Department of EEE at Sri Ramakrishna Engineering College, Coimbatore. She is also having an additional responsibility as a director, Internal Quality Assurance Cell of the institution and professor in charge for the Bureau of Overseas Education. Her main research interests are power system analysis, power system optimization, and renewable energy storage systems. She has published her research work in many international journals and conferences. She has also visited many countries like Malaysia, Singapore, Thailand, Indonesia for her academic and research purpose. She is a recognized PhD supervisor of Anna University, Chennai. Under her guidance, she has produced 5 PhD degrees and currently she is supervising 9 PhD scholars. She has published around 150 papers in various international journals and conferences to her credit. She is constantly organizing various events like faculty development programs, seminars, and workshops for the benefit of the faculty and the student community. She is a certified resource person of National Board of Accreditation, New Delhi, and has conducted many workshops and guest lectures on outcome-based education and outcome-based accreditation. She is also a certified auditor of a National Board of Accreditation and helped many institutions to face the NBA committees by conducting mock audits and providing suggestions for improvements. She is a member of IEEE and a life member of ISTE. She is a recipient of the following awards: an international award instituted by the Venus Foundation, Distinguished Women in Engineering in the field of electrical and electronics engineering. She also bagged the award Best Teacher instituted by Institute for Exploring Advances in Engineering. It's a great pleasure to have you, ma'am. The session is yours. Thank you, ma'am.
Thank you, Mrs. Abhinaya. Thanks for that brief introduction. A warm welcome to all of you for this day 2 of the webinar series organized by the New Horizon College of Engineering and Sri Ramakrishna Engineering College, Coimbatore. And my appreciations to the coordinators, Dr. Gunapriya, Mr. Karthik, and Mrs. Abhinaya. And thanks to the convener of the event, Dr. Mahesh from New Horizon Engineering College. And I also take the opportunity to welcome and thank all the participants who have passionately registered for this 7 days webinar series jointly organized by NHCE and SREC. So I think without further delay, I will try to share my screen. Very good morning to all of you. The overview of the presentation will be Smart Grids, Distributed Energy Resources, Microgrids, a case study, electric vehicles and grid integration, deregulation in electric markets, challenges in smart grids, industrial, commercial and residential solutions, LVDC, the future scope. So let's think together, what is this smart grid all about? You would have heard about this smart grid and lots of other terminologies that are connected with smart grid, like it could be demand side management, or it could be microgrids, or it could be smart metering systems, or it could be the various technologies that are involved in the smart grid, which also includes the IoT and other kind of things. So why this smart grid and what is the importance of this smart grid? Maybe for the next 1 hour we will be looking into this and we shall think together. The engineering evaluation with time goes like this. So when we start from the 18th century, it is all about the first industries, mechanical and electrical engineering, and that is why even today we call mechanical and electrical engineering as the core branches. And in the 19th century, the automobile industry, the assembly line and mass production came into picture. And in the 20th century, it is all about the electronics and IT, the telecom and PLC, all these stuff came into picture. And now it is all about the smart systems, smart cars, smart machines, cyber physical systems, IoT, whatnot. All these things are coming into picture, and in that we are also having the smart city into the picture. I request the audience to kindly mute your audio because it is giving echo to me. So this is the overall scenario as far as the power sector is concerned, and I'm not going to read all these things. As far as Indian power market and power scenario is concerned, we are the third largest producer of electricity, and we have around 20,000 microgrid projects ongoing. And as far as the smart cities are concerned, there are going to be 100 smart cities at least by 2020. And all these solar, wind, and other biomass, biogas, renewable energy systems are into the market. And because of that, the Indian power sector is also planning for 24 by 7 power to all by 2022, and increase in generation of power and addition in the capacity of the power is also going to happen. But in spite of all these things, we can also see that approximately 30% of the people are not connected to power. This is the real scenario of the Indian electricity uh, market. So this is the global growing electricity demand, and we can see that the number of kilowatt hours of electricity that is being consumed by the customers is going on increasing. This is a small graphical representation which shows from the year 2008 until 2030 a prediction in the future years to come, the demand forecasting in the future years to come. So we can see that it is going to be very, very high as far as the future electricity demands are concerned. And coming to the smart grid, so whenever we talk about smart grid, some of the basic things that we wanted to understand is all about what this market dynamics says. So fuels could be either the conventional or the non-conventional fuel. It could be oil, coal, nuclear, geothermal, biomass, anything, and that has to be converted and that has to be delivered to the customers. And when it is being delivered to the customers, we need to have a affordable, secure, reliable, flexible, and environmentally responsible kind of electricity that is available. Means we need to have the quality power that is being delivered to the customers. So affordable, clean, reliable power should be there, should be made available. And during the conversion, we also need to take care of the efficiency, reliability, emissions, flexibility, and last but not the least, the cost of the electricity that is being involved in order to produce the electricity. So these are the things that are to be taken care of when we talk about the market dynamics. So next we will look into the grid transformation. So you can see here there is a solar farm, there is a biogas, and there is a distributed generation and plug-in hybrid electric vehicles. All these things are available, and we can also see that all these energy that is being generated are being supplied to the city. Here, for example, we have considered city A here, city B here, and we also have the distributed generation and distributed substations and individual farms, and conventional power plant is available. All these things are available, and
अटल
the
भी है ना?
grid.
अटल
The,
का कहो, जिसका कहो,
ये कौन सिखा कर रहा है?
ये डिपार्टमेंट ऑफ इलेक्ट्रॉनिक्स में इंजीनियरिंग
can you
कॉलेज
please, participants, can you please mute your audio? It's disturbing.
का ग्रिड का
Thank you. So this is the interconnected grid, and we can see that how the grid has been transformed into a smart grid with all lot of things that are available. So this is grid transformation, and there are some important drivers when we talk about the smart grids. First and foremost thing is the customer satisfaction, and we also need to take care of all the other things like demand optimization, asset optimization, distribution optimization, and the stability of the grid. That is very very important, and energy security. So we all know about the filtraging and the theft that is happening, and moreover when we talk about the IoT and kind of things, we can expect lots and lots of cyber issues, hacking and other kind of issues. So we need to take care of the security of the grid, and best operational efficiency, and less hazards. All these things are to be taken care of when we talk about the drivers that are important as far as the smart grids are concerned. So in simple terms, we can say that we need to have the secured operation of the grid, and at the same time we can have we need to have only the cost which is very very less. So any customer will be looking for the best solution at the minimal price, and that is what is expected in the smart grids as well. So this slide shows the smart grid towards a digital world. It is nothing but a combo of electrical infrastructure and IT infrastructure. So nowadays, gone are those days like I can claim that I am an electrical engineer. I am not bothered about what is happening in the computer domain, or I am a computer engineer. I am not bothered about what is happening in a electrical sector. So now things are becoming interdisciplinary, and that is the order of the day. And we as electrical engineers, we also wanted to know the nuances in the other domains, so that it could be a combined multidisciplinary teamwork which can arrive at some common conclusions. Similarly, here we have the electrical infrastructure and the information infrastructure, and uh, we know that in electrical infrastructure, we have now started to come out with more and more solutions for renewable energy, and we are also planning to increase the productivity as far as the electrical infrastructure is concerned. And as far as information infrastructure is concerned, they are looking into the ways and means of incorporating all the IT infrastructure into the electrical infrastructure, so that the combined infrastructures could give a secured integration of this smart grid. So efficiency need to be increased, productivity need to be increased, and we have to use lots and lots of renewables as and when it is possible. And consumers has to be empowered, and consumers has to be given with lots and lots of inputs as far as the uh, usage of the smart grid is concerned, and more importantly reduction in CO2 emissions. So this is the combination of electrical infrastructure and information infrastructure. And these are definitions of smart grid. I do not wanted to read this, but it is nothing but an integrated system with communication technology and information technology and electrical engineering put together. So it ensures the grid stability and efficient operation. So whenever we wanted to provide a real smart solutions, these are the things that we wanted to keep in mind, that is power generation, transmission and distribution, industrial and commercial customers, residential and community. So when it comes to power generation, we need to embrace the renewable sources and generation optimization, renewables, microgrids, smart grids, energy storage, all these things comes into picture. Transmission and distribution, one important thing what we wanted to know is the efficiency is to be very, very high and reliability is to be very, very high. And as far as transmission and distribution, either it is for industrial customers or it is for residential community, the asset monitoring and diagnostics are also to be taken care of. And you would have heard about the recent trends in metering systems, the net metering infrastructure, which gives us the overall idea about how much power is being consumed and how much power is being generated, and if at all, if we are going to have our own renewable system, whether we wanted to pay back to the electricity board or the electricity board will be paying back to us, all these things will be available once we have the net metering system into our structure. So next is all about the PMUs. PMUs is a very, very important topic. So PMU is nothing but a phasor measurement unit. And these phasor measurement units are the devices which is used to estimate the magnitude and the phase. And these PMUs are also used to measure the frequency in the power grid. So we know that for grid synchronization, we need to measure the three parameters, and frequency is one of the parameter, voltage is another parameter, and phase is another parameter. So these PMUs are also used to measure the magnitude of the frequency in the power grid. And there are challenges when we talk about smart grid. There are challenges in smart grids. In general, we will be looking into the communication infrastructure. See, we are all electrical engineers and we don't have much of idea about the communication infrastructure. What are the LAN WAN protocols that are to be used in order to find the solutions for the smart grid, as far as the synchronization is concerned, or as far as the reliability is concerned, or as far as the criticality of the data delivery is concerned. So there might be lots and lots of communication networking protocol related issues, and that is one of the major challenges. So here the phase measurement unit measures the phasor values of both current and voltage, and these values will give us the high precision timestamp together with the values of the power frequency change rate, etc. So here you can see in this particular slide, there is a GPS satellite which provides accurate timestamp for grid activity. Why the timestamp comes into picture? It's because of the reason that all the grid are to be integrated. That is what is our topic is also about. So when you wanted to integrate one or more grids, what happens is that the time that is being mapped with one-on-one basis between the grids should be the same. There cannot be even a small mismatch in terms of seconds or minutes, which will affect the synchronization and hence the stability and reliability of the grid connected systems. So nowadays everywhere we can see that all are interconnected systems. It's not it's no more an island type of systems, it's an interconnected systems, because whenever there is going to be a deficit in one of the system, that could be taken care of by the other system which is having a surplus amount of power to be supplied. So here the PMUs are installed in various places, like this is the place where the smart houses are connected, and this is the storage, battery storage, from the small sources of energy like solar or wind energy. And these are the offices wherein we need to have the monitoring of the system. So these phasor measurement units monitor the grid and the different conditions that are happening in the grid for every milliseconds. It is not like for every 2 hours or 3 hours. It is for every milliseconds, in order to have a close watch on what is happening. So this is about the electricity distribution. Gone are those days when we had the one-way power flow. So what is our conventional system? We have a bulk power system. The power is being generated. It is transmitted through the transmission system. We had all the step up, step down kind of transformers, and from those step down transformers, it will be distributed to the individual houses. But now the scenario is, it is no more a one-way power flow. Now I myself, being a consumer, I will be able to have my own solar energy production at my home or in my office, or if I have an electric vehicle, I will be able to store the energy and give back to the grid. And all these things nowadays coming into picture, we are no more consumers, we are prosumers. Means we are able to produce, and at the same time we are able to consume. So now we can generate our own electricity, and hence increase or decrease the demand by ourselves, and store the electricities for use at a later time. Everything is possible. And that is why the electricity distribution system is completely changed, and now it has become a bi-directional flow, and the consumers are no more consumers, we have become prosumers, right? So at every instant of time, uh, generation should be equal to demand is the thumb rule for power system engineers. But nowadays it is like a generation equal to demand plus storage, because now the storage can be used to match the demand, and the from where we will get the storage, from the consumer side itself we will be able to get the storage. So this is a pictorial representation which shows the demand and grid integration, as far as different types of renewable energy systems are concerned, for integration, grid integration. Next, we will look into the distributed energy resources. DER is terminology which is becoming popular nowadays. And distributed energy resources management systems are now slowly penetrating into the energy sector, energy market, etc. And this is nothing but a real-time communication infrastructure. And this monitors, controls, coordinates, and manage the distributed energy assets connected at the utility level. So in this slide, you can see that you have the generation, you have the storage, you have the load changes. So in generation, it could be a conventional or a renewable energy resources, solar, PV, wind, or diesel, say for example. And as far as load changes are concerned, we need to look into the demand side responses, energy efficiency, and building up of microgrids. And storage could be battery storage or electric vehicles or fuel cells. Some of the good examples of distributed generation are all our solar photovoltaic panels, wind, hydropower, biomass, solid waste management. All these things will come under the distributed energy resources. So the four important terminology what we wanted to understand in the distributed energy resources are reliability, stability, resilience, and flexibility. So, reliability, we all know, continuous availability of the supply. Stability is nothing but how stable our grid connected system is and how quickly it is capable of coming back to the equilibrium as and when there is going to be any problem in the grid connection. What is this grid resilience? It's a new terminology, right? And of course flexibility is high renewables will be able to cater to the flexible loads and it has to match the supply and demand. And what is this resilience? Resilience is nothing but we have to strengthen the grid resilience. We can also say that the ability to minimize the consequences of handling the extreme weather conditions are sometime back we were talking about the security. It could be a cyber attack or it could be a malicious physical attack. Whatever it is, the resilience has to be taken care of. And these kind of threats and these kind of cyber attacks are quite common when we are talking about the smart grid, because it is going to have lots and lots of data and all these data are available to all the users, and it is easily it could be hacked by the hackers. And to continue with the distributed energy resources, the technical goals, we can also say that it's a combination of technical and economic goals. Uh, these are the things are to be addressed. These every one of these topics are uh, important as far as electrical engineers are concerned, and every one of these topic can lead to a PhD degree as well. How am I going to minimize the distribution loss in the interconnected systems? How the support for the voltage could be provided? How am I going to reduce the peak demand? Each one of these things are important as far as the technical goals are concerned. And when it comes to economic goals, we have to minimize the power purchase of power, the cost that is involved in the purchase of power, and how to minimize the uh, amount that is involved in the transmission and distribution of the power. All these things are challenges as far as the integrated grid connected systems are concerned. We will move on to microgrids. Microgrids are very, very interesting topics, and here I wish to present a case study which will be very easy to understand for each one of you. Before moving into that, let us look into what is a smart microgrid. It's a microgrid when it becomes a smart. It is called as a smart microgrid. A miniature of the conventional grid is the microgrid. It has to be synchronized with the local loads, storage modules, generation systems, etc. And it should be capable of meeting the local demand independently, and it should be capable of measuring all the real-time parameters. In simple words, microgrids are nothing but a smaller version of the traditional conventional power grid. And the one more difference is that these microgrids will be available in the closer proximity between the generation and the user, the customer. So that there are two advantages. Efficiency will be increasing, and second advantage is that the transmission losses are reduced. The main disadvantage of the transmission system is that we have the transmission losses that could be minimized when we have this microgrids in the closer proximity between the loads and the generation place. Okay, this gives you a big picture of microgrids. You can see that maybe the customer is having a wind turbine, energy storage, solar, biomass, biogas, whatsoever it is, and they are planning to supply the power to the nearby industry or to the housing area. The advantage is that the transmission cost and losses are avoided. So that is the very bigger advantage. We will just see uh, a small 6-bus system. You can see this is a microgrid where we have the buses, and each of the bus, that could be a generator bus or a load bus, they are connected with the loads, and there is a, pumped hydro, and there is a variable speed drive also connected. There is a wind power production is happening. So this is a very simple microgrid. So I will show how this microgrid could be converted into a smart microgrid. So this is a simple conventional microgrid, and now when we wanted to convert this existing microgrid as a interconnected grid system, what happens is everything remains same. To the bus one, I am going to connect to the system is connected to the grid, and hence now it has become a grid connected system, right? And when I wanted to again convert this into a smart microgrid, what happens is that, see, whenever a system wants to be smarter, we wanted to have the data collection, we wanted to have the analysis of the data that is being collected, we wanted to have the complete control of the system. So in order to have that, what we are doing is that we will be having the real-time data collector unit. So this real-time data collector unit is being connected wherever required. In this, you can see that there are 9 real-time data collector unit, and each of those things are connected either to the bus or to the charge controller, or to the solar PV. Wherever it is required to monitor, it is being connected. Now our microgrid has become a smart microgrid. Now it has been converted into a DEMS enabled smart grid, that is distributed energy management system enabled smart grid. So what we are actually doing is that we have all these RTDCUs, and these RTDCUs are connected to the distributed energy management system, wherein we will be having the overall data collection and analysis of the data. So the existing conventional smart grid has been microgrid has been converted into a smart grid, and the smart grid has been converted into a DEMS enabled smart grid. So these are some of the parameters that we could measure, that is whether our the generated power is being supplied or imported from the grid or exported to the grid, or there is going to be no exchange. Similarly, is the status of the local load, whether the power is consumed or power is not consumed, and for each and everything we have given the conditions. For example, the status of the battery. If it is charging, it will be indicated as 1. It will be discharging, it will be indicated as -1. If it is simply disconnected, it is not being used, it will be indicated as 0. So these are some of the parameters that could be measured by using this smart grid enabled parameters and in the grid connected mode. Similarly, you can also see that the status of frequency. We wanted to monitor the frequency. We want to have the frequency always equal to 50 hertz. If it is less than 50 hertz, it is indicated as 1. If it is greater than 50 hertz, it is indicated as -1. If it is equal to 50 hertz, it is indicated as 0. So, the distributed energy management decisions in the grid connected mode, depending upon the parameters, the suggestions will be provided and it could be incorporated. Whether we wanted to maintain the same state or whether we wanted to charge the battery or discharge the battery, whatsoever it may be, it could be the decisions could be taken and it could be implemented. So up to now we have discussed about the fundamentals of grid connected systems and what is distributed energy management systems, and we have also looked into what is the phasor measurement unit and how it could be used, and we had a case study how to convert an existing microgrid into a smart DEMS controlled microgrid. Next, we will move on to the interesting topic, which is the order of the day, the electric vehicles and grid integration. So, all of us know that India is planning for electric vehicles, and these are some of the pictures of electric vehicles. We have starting from uh, two-wheeler up to transport bus. We have the electric vehicles in place, and these are some of the pictures showing the various electric vehicles in the Indian market, whether it is a in-house product like Mahindra e-Verito or it is an imported model Hyundai. All these things are available, and various charging are also available. So why I am talking about this vehicle technologies here, because in a grid integration, it is possible to have the vehicle to grid technologies which allows the bidirectional energy exchange between the electric vehicles and the power grid. So it could be a AC charging or a DC charging. It is possible for us to have the a grid connected system, that is electric vehicle could be integrated with the grid, and we can also look into the possibilities of having the grid regulation and providing a spinning reserve, or taking care of the peak load shaving or reactive power compensation. Each and everything is possible by using the vehicle to grid integration. So, this is the EV's charging behavior. The charging strategies could be either uncontrolled charging or a controlled charging. And when it comes to uncontrolled charging, we have dumb charging or informative charging. And in controlled charging, we can have unidirectional charging or bidirectional charging. And in this bidirectional charging, we have the V to G technique. V to G is nothing but vehicle to grid technology. So here you can see the grid is the electric vehicle is being connected to the grid, and vehicle to grid technology describes the possibility wherein the electric vehicles, either it is a battery electric vehicle or it is a plug-in hybrid electric vehicle, they will be able to supply or sell the demand response services to the grid, or it can take the power from the grid. Both the ways it is possible, and this slide shows the unidirectional wherein we get the power from the grid, but this slide shows the bidirectional wherein we are using the energy that is being stored to give back to the grid and also to take back from the grid. So the storage capabilities can enable the electric vehicles to store and also to discharge the electricity generated from the renewable energy sources, and it will be helping the grid stability as well. So this is bidirectional charging, which is V to G, that is vehicle to grid and grid to vehicle. So quite some time back, there was a question: will EV penetration impact on the grid? Will the EVs break the grid? So these are the questions 4 5 years before it popped up. But the present scenario of e-mobility is that Indian government is planning to switch all the cars to electric cars by at least 2030, and 100% of EV for public transport. And any power engineer, you might be knowing about the deregulation in the power system. So nowadays it is no more a monopoly like generation, transmission, distribution, and supplying it to the customers. This is the monopoly structure earlier where what has been practiced, but nowadays it is not like that. We have the Gencos, Transcos, Discos, all those things which are aiding for the reduction of the electricity price, and also development of the innovation as far as the grid integration is concerned. So power quality challenges are also there when we talk about the grid integration. So these are the terminologies which are quite commonly used by the power engineers: harmonics, sag, swell, voltage imbalance, etc. So whenever we have the grid integration along with the EV, these are the things that are also to be addressed. And EV, whether it is possible for the EV to strengthen the grid. Okay, we all must understand that our electric cars, if we have an electric car and we are going to charge that electric car, we will be using the energy whatever is required, and the excess energy, if it is connected to the grid, that could be paying us back by the electricity board people. So that is what is being written here. Why charging your electric car at night would save the world? Because it is possible for us to give back to the grid. And also there is another news: parked electric cars can earn $1,530 from the power grids. This is also going to be in place as far as the Indian electricity market is concerned, maybe down the line another 5 years. If you own an electric car and if you are capable of connecting your car to the grid, the excess energy that is available in your car could be transferred to the grid and the EV people will pay you back. That is what is the scenario, maybe in another 4 5 years. So this is the driving pattern. And this is again, the EV could also be visualized as a virtual power plant, which could be capable of giving the power back to the grid. So EV as a grid, EV can provide grid services. So you can see here we have the power grid where you have all the voltage regulation, frequency regulation, and all those things. And you have the loads, the EV loads that are connected on the right hand side. So bidirectional communication of supplying from grid to vehicle and also from vehicle to grid is absolutely possible. So challenges for vehicle to grid technology. I don't want to read all these challenges. One or two things I will let you know. Security, as far as the energy and information security, that is one of the major challenge. Robust smart electricity grid which need to maintain the reliability, flexibility, extendability, etc. And government policies that are to be specifically brought in. Cyber and physical threats, all these things are challenges. So next 2 3 minutes we will look into the industrial and commercial customers. When we talk about the industrial and commercial customers, these are the things that are to be taken care of: asset monitoring and diagnostics, advanced metering infrastructure, that is net metering, distributed generation infrastructure, backup power management and control, time of use reporting, and energy management during the islanded operation. Smart metering facility, this is the future. Bidirectional power flow, net zero energy. At defined time intervals, it is capable of having automatic metering capability. And advanced metering system, it is possible for us to have remote access, advanced measurement, and communication with the home appliances, the smart homes kind of things. And when it comes to residential and community, we have the advanced metering infrastructure, distributed generation infrastructure, smart appliances, home energy use monitoring, and LVDC. So we will spend another 2-3 minutes in the LVDC, that is low voltage DC for homes, buildings, and microgrids. So LVDC motivation is that a large number of appliances in the households, offices, and industries could be able to run internally on a low voltage DC. So just have a look at what all the appliances we have that will be possible to run on a low voltage DC. And higher distributed generation from solar. So there is no necessity to again convert into AC. Straight away, intrinsically, it could be used for DC. And ease of integration and compatibility of DC distributed generation with energy storage solutions, and efficient power supply. Most importantly, the power consumption is very less when we go for LVDC, and this is the motivation for usage of LVDC. AC/DC comparison, AC model, distribution line, AC load transformer, capacitor for war compensation, and in DC model, again you have the distribution line. Instead of AC load, we have the DC load. We don't have the transformer, there is no necessity for that, and war compensation. Instead, we have the DC-DC converter. So, transformer is the bulky equipment, all of us know, and that is not necessary when we talk about a DC model. So, here we have the solar photovoltaic modules given to the load. So, it is a simple solar direct systems. That is, that could be a solution through LVDC. If it is a standalone DC system, we have the PV modules, we have a charge controller, a battery, then it is connected to the DC load. That is also possible with the LVDC. If it is a standalone AC system, PV modules, charge controller, battery, again that could be given to the remote homes or a non-grid connected systems. So LVDC could be a better solution for microgrids, for homes, and for places where we have small loads. So this is how the future home will look like. All the apparatus that we are using would be of whatever the apparatus we are using, that would be of high rating capacity. We will be having our own solar PV panels installed in our premises, and dimmable LED or CFL lighting will be used, and demand side management will be uh, perfectly taken care of. Net metering facility, which will be connecting the utility and the customer, and of course every one of us, we will be having the plug-in hybrid electric vehicles, which will be grid connected, and we will be able to support the centralized grid. So this is how the future home will look like. And to summarize whatever we have discussed, the marriage between the IT engineers and the electrical infrastructure to support the energy needs by increasing the various efficiency is the smart grid. So what are all the different efficiency that are to be taken care of? The resource efficiency means it could be a solar PV installed in the rooftop, or it could be a wind mill, a small windmill, or it could be a plug-in electric vehicle, and all this is possible. Energy efficiency, advanced controls to reduce the transmission and distribution losses. Consumer efficiency, the consumers will be able to manage energy usage and costs without compromising their lifestyle. Asset efficiency, in order to monitor and to fully utilize and extend the life of the available assets. Operating efficiency, remote monitoring and control, and to improve the reliability, resilience, stability, resource utilization, etc. So overall, by having this grid integration, even though we have lots and lots of challenges, if at all, if it is possible for us to arrive at the solutions for these challenges, and lot of research is happening. A lot of PhD works are also happening in this particular domain of grid integration and renewable energy systems and optimization techniques. So, the integration of IT infrastructure and the electrical infrastructure has led to this. And we, as electrical engineers, we should not have any hesitation to understand the IT infrastructure and communication infrastructure, LAN WAN protocols, and data acquisition, about the sensors and big picture of what is happening in all these things. So, this will definitely lead to a wonderful scenario of the power sector, the Indian power sector in near future. I'm done with my presentation. Thank you. Thanks for the opportunity provided. And any queries, I am ready to answer.
Thank you so much, ma'am, for the wonderful session on the renewable energy grid integration techniques and its challenges. Participants, if you have any queries, you can ask her, ma'am. I think there are no queries, ma'am. Thank you so much, ma'am, for such a wonderful session.
Thank you. Thank you, Mrs. Abhinaya. Thank you, Mr. Karthik. And thanks, Dr. Gunapriya, for providing this opportunity for the wonderful participants during this webinar series.
Thank you, ma'am. Thank you.
Thank you.
Thank you, ma'am.
Thank you, Karthik. Shall I leave the session?
Yes, ma'am. Yes, you can leave, ma'am. Thank
Yeah,
you.
thank you. Thank you all. Thanks.